In a recent development that has sent ripples through the energy sector, an independent German teardown of a commercial sodium-ion battery from China has revealed surprising results. Researchers found that this battery performs far better than expected, reaching production quality and design features directly comparable to those found in Tesla's renowned lithium-ion batteries. This unexpected parity suggests a significant leap in battery technology, challenging long-held assumptions about the viability and immediate future of sodium-ion alternatives. The findings compel a closer look at the strategic implications, particularly in areas beyond consumer electronics. For years, lithium-ion batteries have dominated the portable energy market, but their reliance on finite and geographically concentrated lithium resources presents a strategic vulnerability. Sodium-ion batteries, conversely, utilize sodium, an element far more abundant and widely distributed across the globe, primarily extracted from common salt. While sodium-ion technology has historically lagged in energy density and performance compared to lithium, this new Chinese breakthrough changes the calculus. The question now becomes, how close has it come to challenging lithium-ion supremacy, and what specific attributes make this particular iteration so remarkable, especially for demanding applications? The battery at the center of this investigation comes from Chinese manufacturer Hina. According to an independent teardown published in the Cell Press journal Cell Reports Physical Science, Hina's commercially deployed sodium-ion cell was meticulously disassembled and analyzed. This detailed examination was performed by German scientists, lending an impartial, third-party validation to the claims. Their findings were not merely anecdotal but based on a thorough engineering analysis of the cell's construction and material science. This scientific rigor is crucial for substantiating such significant technological comparisons. What shocked researchers was not just that Hina's sodium-ion battery performed well, but that its production quality and internal design were broadly comparable to Tesla's lithium-ion batteries. This assessment extends to key benchmarks, including manufacturing precision and the uniformity of the cells. As one researcher, Schutte, noted, "We were positively surprised by how uniform the cells are." This uniformity is a critical indicator of high-quality manufacturing, suggesting consistency and reliability across a production batch, qualities essential for widespread adoption and trust in advanced technology, particularly in high-stakes applications. The secret to this performance parity lies in the battery's sophisticated internal architecture. The Hina sodium-ion battery employs a double aluminum design, which is a significant innovation. This particular layout is engineered to lower electrical resistance within the cell, directly contributing to more efficient power delivery. Furthermore, it promotes a more even temperature distribution throughout the battery, enhancing both safety and longevity. Crucially, this advanced internal structure closely resembles the architecture currently used in Tesla's high-performance lithium-ion batteries, underscoring the engineering sophistication achieved by Hina. Beyond structural similarities, Hina's sodium battery demonstrates impressive performance metrics. Researchers noted its high power capability, suggesting it can deliver significant bursts of energy when needed. Equally important is its strong low-temperature performance, an attribute that makes these cells particularly attractive for stationary storage applications, and potentially for demanding mobile scenarios in varied climates. While initial reports highlighted its potential for stationary storage, these characteristics are also highly relevant for military equipment operating in extreme conditions, where consistent power output is non-negotiable. Despite these advancements, the Chinese sodium-ion battery still faces areas for improvement. Researchers point to cold weather charging and overall energy density as key challenges. Currently, lithium-ion batteries generally hold an edge in these specific parameters. However, the potential for improvement is significant. Engineers are actively working to tweak the new battery to charge more effectively at low temperatures and to function better at higher energy densities. If these improvements can be realized, sodium-ion technology could truly become a formidable rival to lithium-ion, not just in cost-sensitive applications but across the board, including military uses. The most compelling advantage of sodium-ion batteries, beyond their evolving performance, lies in their potential for low-cost and abundant resource availability. Sodium, unlike lithium, is not a rare earth element, it is globally plentiful and inexpensive to source. This fundamental difference means that once scaled, sodium batteries could significantly undercut the price of their lithium counterparts. For China, the world's largest manufacturing economy and exporter of goods, this economic incentive is massive. Furthermore, the ability to leverage an abundant domestic resource provides a strategic hedge against supply chain volatility and dependency. For any major industrial power, reliance on foreign-controlled resources represents a strategic vulnerability. China, despite its status as the world's manufacturing superpower, has significant dependencies, particularly on critical raw materials like lithium. The global lithium supply chain is heavily influenced, if not outright controlled, by Western allies. This geopolitical reality means that in times of tension or conflict, China's access to essential battery components could be curtailed, impacting its economic and military capabilities. The development of viable sodium-ion technology directly addresses this critical national security concern. China's role as the factory of the world and the largest manufacturing industrial economy is not just an economic descriptor, it's a strategic asset. This immense manufacturing capacity positions China uniquely to rapidly scale up the production of new technologies like sodium-ion batteries. With established industrial infrastructure and a skilled workforce, the transition from research breakthroughs to mass production can happen at an unprecedented pace. This capability is vital for integrating new energy solutions into diverse applications, from consumer electronics to advanced military hardware, bypassing reliance on external manufacturing capabilities. The implications of a robust, cost-effective sodium-ion battery technology for military applications are profound, starting with electric combat vehicles. Future battlefield scenarios envision fleets of electric tanks, armored personnel carriers, and logistical support vehicles. These vehicles require immense power for propulsion, onboard systems, and defensive measures. Traditional battery chemistries often face limitations in terms of weight, volume, and supply chain vulnerability. Sodium-ion's emerging capabilities could directly address these challenges, offering a domestic and strategically secure power source for next-generation ground forces. One of the most critical aspects of military operations is endurance. For electric combat vehicles, battery life translates directly into mission duration and operational range. Sodium-ion batteries, with their high power capability and increasingly competitive energy density, could significantly extend the time military vehicles can operate without needing to recharge or refuel. This enhanced endurance means fewer logistical stops, greater flexibility in tactical deployment, and sustained presence in contested areas. The ability to maintain operational tempo without constant resupply is a decisive advantage in modern warfare, reducing exposure to enemy threats. Beyond raw power and endurance, electric combat vehicles powered by advanced batteries like sodium-ion offer a significant tactical advantage: silent operation. Unlike combustion engines that generate considerable noise and heat signatures, electric motors are remarkably quiet, reducing acoustic detection and thermal visibility. This stealth capability is invaluable for reconnaissance missions, special operations, and surprise attacks, allowing forces to approach enemy positions with a much lower probability of detection. This attribute fundamentally changes the dynamics of close-quarters combat and covert infiltration scenarios, providing a silent edge on the modern battlefield. Perhaps no military application is as rapidly evolving as drone warfare, particularly the concept of drone swarms. These autonomous or semi-autonomous groups of drones require sustained power for extended missions, particularly when operating far from base. Current battery limitations often restrict their operational range and loitering time. Sodium-ion batteries, with their high power capability and strong low-temperature performance, could provide the necessary energy density and robustness to significantly increase drone swarm endurance. This would allow for longer surveillance missions, sustained reconnaissance, and more complex, multi-layered attacks, transforming their utility. The effectiveness of a drone swarm is directly proportional to its ability to operate cohesively and for extended periods. With enhanced battery endurance from sodium-ion technology, drone swarms could conduct sustained operations over wider areas, providing persistent intelligence, surveillance, and reconnaissance (ISR) capabilities. They could also maintain presence in contested airspace for longer, effectively overwhelming enemy defenses with continuous pressure. This sustained operational capability would move drone swarms from a tactical novelty to a strategic game-changer, enabling truly persistent air superiority or denial over vast stretches of territory without constant human intervention. Beyond vehicles and drones, the logistical burden of powering military operations in the field is immense. Soldiers operating in remote areas, forward operating bases, and disaster relief zones require reliable, portable power for communications, medical equipment, and personal gear. Current solutions often involve noisy, fuel-hungry generators that are difficult to transport and maintain. Sodium-ion batteries, once optimized for energy density, offer a compelling alternative. Their potential for lower cost and reliance on globally abundant sodium makes them ideal for scalable, robust, and easily deployable portable field power systems, reducing logistical complexity. The reliance on fossil fuels for generators in the field creates a significant vulnerability. Fuel convoys are prime targets for adversaries, and the logistics of transporting fuel to remote locations are complex and resource-intensive. By transitioning to sodium-ion-powered portable systems, military forces could drastically reduce their fuel dependency. This not only enhances force protection by minimizing vulnerable supply lines but also simplifies logistical planning, frees up transport assets, and reduces operational costs. The ability to generate or store power from non-fuel sources becomes a strategic asset in prolonged engagements, lessening the overall military footprint. Perhaps the most significant strategic implication of China's sodium-ion breakthrough is the profound impact on its supply chain resilience. For too long, China's advanced technology sector, including its burgeoning electric vehicle and electronics industries, has been reliant on lithium. This reliance meant susceptibility to geopolitical pressures and supply disruptions, especially from Western allies who often control key lithium mining and processing facilities. By developing a domestic, high-performance alternative based on abundant sodium, China can dramatically reduce this dependency, strengthening its strategic autonomy and insulating its military and industrial capabilities from external leverage. The mere abundance of sodium, found in vast quantities worldwide and easily accessible, transforms it into a strategic asset. Unlike lithium, which is concentrated in specific regions and often requires complex political negotiations or foreign investment to secure, sodium offers a pathway to energy independence that is almost unprecedented. For China, leveraging this ubiquitous element means less reliance on foreign imports and a more secure, domestically sourced supply for its critical battery needs. This shift fundamentally alters the resource competition landscape, providing China with an intrinsic advantage that other nations, dependent on lithium, may lack. A commercially viable, high-performance sodium-ion battery from China could reshape the global resource competition. For decades, nations have vied for control over strategic resources like oil, rare earth elements, and more recently, lithium. If sodium-ion becomes a widespread, cost-effective alternative, the intense geopolitical pressure surrounding lithium extraction and supply chains could ease. However, it also means China could gain a new, independent advantage, potentially shifting the balance of power in material science and energy storage. Nations that do not develop similar indigenous battery technologies may find themselves at a strategic disadvantage. China's established position as the world's largest manufacturing industrial economy, often referred to as the factory of the world, gives it a unique capability to scale this sodium-ion breakthrough rapidly. The infrastructure, supply chains, and skilled workforce already exist to transition from research to mass production at an unparalleled pace. This means that China could potentially deploy sodium-ion batteries in a wide array of applications, including military systems, far faster than other nations. This manufacturing prowess translates directly into a strategic advantage, allowing for swift integration of new energy solutions into its defense capabilities. Energy storage breakthroughs, like this sodium-ion advancement, inherently possess a dual-use nature. While initially targeting commercial electric vehicles and grid storage, the underlying technology can be seamlessly adapted for military purposes. The same principles that make a battery efficient for an EV or a stationary storage unit also apply to an electric tank, a drone, or a field power system. This convergence of civilian and military technological development allows for rapid advancements in defense capabilities, often benefiting from the scale and innovation driven by commercial markets, accelerating the pace of military modernization. While the low-cost potential of sodium-ion batteries is a significant driver, the strategic imperative for China extends far beyond mere economics. Reducing vulnerability to external supply chain disruptions is paramount for national security. A military powered by batteries reliant on foreign-controlled rare earth minerals faces inherent limitations in times of geopolitical friction. By developing and deploying a domestic, sodium-based alternative, China fundamentally de-risks its military posture, ensuring continuity of operations and resilience against embargoes or blockades. This shift underscores a broader strategy of self-sufficiency in critical technologies. The long-term geopolitical ramifications of China's sodium-ion breakthrough are complex and far-reaching. It could alter the calculus of resource diplomacy, diminishing the leverage held by nations controlling lithium supplies. It empowers China to project its military and economic influence with greater independence, reducing reliance on the global liberal order for critical components. This technological leap contributes to a multipolar world where energy independence translates into strategic power. The race for energy storage dominance is not just about cleaner energy, it's about who controls the future of industrial and military power, and China just made a significant move. The HENA sodium-ion battery breakthrough marks not just an incremental improvement, but potentially the dawn of a new era in energy storage. While lithium-ion batteries will undoubtedly remain crucial for high-performance, weight-sensitive applications for some time, the emergence of a cost-effective, high-quality alternative fundamentally expands the possibilities. It offers a scalable solution for a broader range of needs, particularly where abundant resources and economic viability are paramount. This development broadens the spectrum of viable energy storage solutions, driving innovation and competition across the entire industry, pushing the boundaries of what is technologically feasible. Despite its promising advancements, the path forward for sodium-ion technology involves continued research and development. Addressing challenges such as cold weather charging and further increasing energy density will be critical for its widespread adoption, especially in military contexts. However, the foundational achievement of matching Tesla's manufacturing quality and internal design is a powerful indicator of its potential. With China's massive manufacturing capabilities and strategic focus, these remaining hurdles are likely to be vigorously pursued. The speed at which these improvements manifest will dictate the timeline for sodium-ion's true disruptive impact on both commercial and military sectors. In an era defined by technological competition and strategic rivalry, China's sodium-ion battery breakthrough represents a significant step towards rebalancing global power dynamics. By gaining greater energy independence and reducing reliance on external supply chains for critical military and industrial applications, China enhances its strategic leverage. This move challenges the existing order where control over specific resources translated directly into geopolitical influence. As China continues to innovate and scale, its ability to domestically produce advanced energy storage solutions will be a powerful force in shaping the future of global alliances and military capabilities. To summarize, the Chinese sodium-ion battery breakthrough promises to revolutionize military energy storage across several key fronts. For electric combat vehicles, it means enhanced battlefield endurance and silent operation. For drone swarms, it translates to significantly extended mission profiles and sustained operational presence. For portable field power systems, it offers reliable, low-cost power, reducing fuel dependency and logistical vulnerabilities. Most crucially, this technology provides China with a pathway to reducing its strategic dependence on lithium supply chains, which are largely controlled by Western allies, fundamentally bolstering its national security and strategic autonomy. Ultimately, this technological leap provides China with a profound strategic advantage. As the world's manufacturing superpower, China is uniquely positioned to rapidly integrate and scale this indigenous battery technology into its vast industrial and military complex. This capability ensures that future generations of Chinese military hardware will be powered by secure, domestically sourced energy, free from the constraints of foreign supply chains. The ability to innovate and mass-produce such a critical component independently transforms a perceived vulnerability into a decisive strength, solidifying China's position as a major player in the global technology and defense landscape.